right? So now we're doing convolutional neural networks. So here you start with first reading the data. So as I said, this is the MNIST data. So you have this, pixel values. So 784 pixels, right? And you have 42,000 images, right? So this is what you have, right? In your training data, in your testing data, you have 28,000 images of 784 pixels each, right? Okay. So these are some pre-processing steps. This is how an image looks like. This is an image of a one. Okay. So if you can see, this is a bit tilted, but your model should be robust enough to, you know, identify this identifies this number. Okay. Okay. Similarly, now what you do is that you pass your pixels of all these images that you have. So let's say these are the pixel values of the image that you have. So what you do, you convolve it with a filter. So this is what is called filter is a smaller matrix. So in this case, you see the image is 7 cross 7 image, and your filter is a 3 cross 3 image. So you convert this by convolution. I mean you just multiply the filter with the source pixel, pixel by pixel, basically source image pixel by pixel. For example, you multiply 0 by 4, then again this 0 by 0, this 0 with 0, and again do the remaining things, add them all up. So this is what is taking place, and the addition adds up to -8, and value of -8 over here somewhere in the middle. Okay, and then you shift this filter one step at a time, and you calculate what is the convolution value, and you do you know make a new matrix, new uh, reduced dimension pixelated value. Okay, you obtain a new image with a reduced dimension. Okay, this is the new pixel value. Okay, so this is the first step that we saw in our slide. So if you see in this image, so this is the convolution. Okay, first convolution plus ReLU. So you just put this whatever value that you get. So this is, let's say, one of the convolved image. You pass these values, all these values, to this ReLU function. So what ReLU function does is, as I said, if the value is greater than 0, it takes that value. So 15 greater than 0 is 15, whereas -110, it reduces it to 0, right? And that's the convolution plus ReLU. And this is the padding step. So I will not explain. You should look at what this step does. I will not explain it here. And this is one of your homeworks. So after padding, what you do is that you pool the features. So for example, pooling could be, it could be max pooling, mean pooling. So in this case, we are doing max pooling. For example, you take the set of 4 pixels and check what is the maximum of these 4 pixels. So 2, 2, 3, and 1.5. So 3 is the maximum. You put the maximum value over here. Similarly, you do it for all the remaining. So 5 is the maximum, 5 you do. So that is the pooling. Okay. And then flattening. What you do is, after you do the pooling, you flatten the data. So basically, if you have 1, 2, 3, 4, you flatten it as 1, 2, 3, 4. So just make it a column. And then you put this column in the input layer. And then you do the conventional neural networks that you have, right? And so on. So this is the flattening step. This is the uh, neural network dense layer steps. So these are called basically dense layers. Okay. So if you see, this is where we build the model, right? So for example, we start with the sequential model. We add the convolution filters with 8, filter size is 8. Sorry, kernel size is 5.5. We need 8 filters. We use the activation ReLU function. Your input dimension shape is this. And after that, you add a pooling layer, pooling size of 2 cross 2. And then you add a dropout layer. So dropout is something which is also very important. So instead of keeping, so let's say, so they did the dropout after max pooling. So what happens after max pooling? So if you have the pooled feature, so instead of using all the features, you can drop out some of the features. So let's say you drop out the second pixel and the third pixel, right? So in this way, you can drop out some of the pixels. So here 0.25, that means 25% of the pixels will be dropped out. So that is another dimensionality reduction step that's happening over here. And then again, you add another convolution, another pooling layer, another dropout, and finally you flatten the data, and then you add dense steps, and again dropout, and again another dense step. So by the dense step, I mean this hidden layers that you include. So in the first dense step, you use the activation function. So this summarizes you of all the things that you have. For example, what is the input size of the first step, 28 cross 28 cross 8, and then what is the details of the max pooling dropout, and so on. Okay, and finally, so see, so this is again, you use the optimizer. What is the optimizer that you are going to use? Atom optimizer. This is just for gradient descent. This is your learning rate. So beta 1 and beta 2 are some of the parameters that you need while using the atom optimizer. So what the atom optimizer does is it uses a weighted, it uses the, so for example, if let's say your learning rate is uh, in this iteration is something, and in the previous iteration it was something else. So it's a dynamic learning rate. Your learning rate is not always constant. Based on beta 1 and beta 2, your learning rate will get modified, right? And then you compile your model using this optimizer, and using the loss function as category cross entropy, and you use the matrix accuracy, right? And this is the data augmentation step. So data augmentation, and what we do is that you basically take your original data and you transform your data. Maybe for example, let's say rotate it. So this 6 you see, you rotate this 6 so that your model can see all the variations of this number 6. So it can identify rotated 6 as well, not only when the 6 is written in the straight way. So this is an example of data augmentation. And then finally you fit the model in, and you train it. So for example, here we have and epochs 10, and this is your validation data, and we finally you fit the model. So this is going to take a while uh, till you fit the model. Let me make the epoch size a little lower. Maybe then it will be faster. So let's take epochs equals to 1. Okay. Okay. So it will just do for one epoch. But you see, if you take more and more autoencoder example, right? For example, when you are going into the first epoch, your loss is 0.03. And then as you go into further and further epochs, your loss, basically your error decreases, right? That you see over here. So that's why we need to have more and more epochs, right? But you can try it out. I will have the notebook, and this is the, you see, this is the loss function. So you have 60% error, right? So your accuracy is 80%. To improve the accuracy, you have to, you know, uh, do more. Confusion matrix is explained in one. So I'll just quickly say that, okay, this row means that this is actually 9 and also predicted as 9. So you have 386 samples which are actually 9. You have 8 samples which are actually 9 but are predicted as 7, right? Accuracy and so on by using